Yes, it's a different talk than the one I gave in London, and I have a little interesting story about that London talk. The first comedian over there is Russell Brand, the British comedian, and when I was sitting in that venue, which is about the same size, back this way? Yeah, for the fan, sorry. This is going to go great. Anyway, there was they also had a coffee shop. Wow, hang on. Operator error here. They also had a coffee shop next door, and I was sitting in the back one day, and all of a sudden the door opened, and Russell Brand popped his head in to see what all the fuss was about. In fact, Ben was speaking at the time. I think Ben, yeah, you remember seeing him. So anyway, it's a small world. All right. So I'm going to talk a little bit about what error handling means in reactive systems. I've already put this talk on my polyglot programming site, and it's actually also on SlideShare. And what I do at TypeSafe is I work on big data problems, Spark and so forth, so that's sort of my thing right now. But, you know, we have this Reactive Manifesto, right? And there's these 4 horsemen of the apocalypse that we're supposed to be worried about. And in particular, in the resilient trait, we're supposed to treat errors as first-class citizens. Ben did a great job talking about this at Netflix. You know, errors are just facts of life. They're not exciting. They're not interesting. They're just something that is, you know, as important as actually delivering videos or whatever. It's just something that's part of the system. So what this talk is about really is, well, how well are we doing with some of our reactive systems? How well do they actually treat errors or failures as first-class citizens? And if they don't, what could we do better? I'm kind of going to follow a little bit of some of the outline of this book, which is Debashis Ghosh's new book. There's only 2 chapters available, but it's going to be a really great book on updating domain-driven design, so I really recommend this book. And it's actually right now the top-selling MEP on Manning, I happen to notice today. But anyway, just a shout-out to this book. Well, the first thing we could do is we could obviously mix error handling with our domain logic, you know, just as part of the setup for whatever it is we're setting up, whether it's reactive streams or whatever, just put in, you know, what do we do if an error happens? And yeah, this actually works pretty well when, you know, we have fairly narrowly focused errors. Like if you're parsing user input and you're going to send back some response that they typed in an integer instead of a string or whatever, that's fine. One of the things Reactive Extensions has is facilities for handling the case where a stream might stop temporarily or be completely stopped. You know, how would you fail over in that case? Yeah, forgot about that fan thing. All right. So I'll even show an example of the last one here, failing over between streams in reactive extensions. But it's kind of limited too. This approach kind of just means you can only handle, you know, one thing at a time, a narrow scope. You know, I've got this stream set up, something goes wrong, what do I do? It's a little hard to implement a larger strategy if all you have are facilities that are native to the API you're using. So to set this up, let's talk about a fundamental principle that's guided a lot of distributed toolkits, which is communicating sequential processes, or CSPs, which were originally formulated back in the 70s by Tony Hoare, and then they were evolved somewhat. And while I think about it, I've actually got a long list of references at the end of the slide deck that I won't show you, but a couple of them are actual free books, one of which written by Tony, that go into this in gory detail. Rob Pike has this great quote, which is really kind of the whole idea, is rather than trying to communicate by sharing memory, in other words, the sort of multi-threaded programming that none of us can do very well, why don't we instead share memory by communicating? So almost all the systems we'll talk about basically take this model. So rather than talk about the theory of CSP, let's talk about some actual implementations that are inspired by it. The first is Go, the Go language, and then the second would be Clojure's core async. The simplest idea that you have is a channel into which you can put values and then pull them out on the other side. And if it's a single element channel, it's blocking, meaning that the put operation is going to block if there's no one on the other side to read it, which is not normally what we want to do, right? But it's our starting point. So there's got to be somebody on the other side to do the get. A nice feature about this is you can type the channel, so you're not allowed to put things in that are not expected. If I'm expecting an integer, you can't give me a string, that sort of thing. But one thing it doesn't specifically prevent you from doing, unless you're careful, is you could pass mutable state and then get into problems of the usual synchronizing of updates. So don't do that if you can avoid it. But on the other hand, it might be that you're doing a handoff where you've got some mutable state to be mutated, but whoever did the last get is the only person allowed to mutate it. So you can do tricks like that. Well, the next step up is to use basically a bounded queue. In this case, I just showed an example of 3, but it could be much bigger if you wanted. And the nice thing about this is that it actually is more asynchronous. As long as there's spaces available in the queue, you can put values into it. But then you've got to decide what to do if you fill it up and there's, it's not being read fast enough on the other end. Well, you could just block, like we did with the single element case. You could drop the newest one, whatever value you were trying to put in there. Or you could treat it like a sliding window where you just drop the oldest. So then obviously you have to decide what makes sense. Well, so far I haven't really talked about concurrency. So what you actually typically do is you wrap these things in what I'm generically calling a Go block. These would be Go routines in the Go language. In Clojure, this would either be a thread that you explicitly allocate, or they have a notion of Go blocks, which are more like a thread pool backed thing. In fact, Go blocks are the only things you can use in Clojure.js because JS is only single-threaded. But it basically gives you the illusion of multi-threads of control, even though behind the scenes it's actually managing who's actually running at any one time on one or whatever number of threads you have available. So this is great because it lets us be asynchronous. It lets us have a channel of arbitrary size. Actually, one thing I didn't mention about the fact that it's a bounded size queue is that you'll never run out of memory. You won't get out of memory errors if you happen to be pumping data in too fast for the consumers. And I like to think of these as kind of analogous to futures, actually, when you're using Go channels. Conceptually, you use them a lot in the same way, if you know futures. And the last bit I'll talk about in this model is the analog of like socket select, where I might have a bunch of sockets I'm listening on, and I call select to see which one has actual data available, and then I trigger some processing. But I don't want to just be watching one channel. I want to be watching several of them. Go actually has a select operation for this. In Clojure's core async, there's what is it called again? And there's an alt operator that's either blocking or not blocking for doing the same thing. So it can either be blocking or non-blocking, and it works like socket select. Well, at this point, neither Go nor core async have actually implemented distributed channels, so it's really still kind of a single process system, maybe running on a thread pool, so multiple threads. And that means that they haven't had to solve a lot of the problems that we get into when we're in truly big distributed systems. So in a way, they haven't really had to face the pain that, say, an actor system's had to deal with yet. But nevertheless, you'll often see people use channels as sort of the way of managing, like blocking resources like I/O or a network access or whatever. So let's talk briefly about how you would do failure handling in core async, just as an example, and it's more or less similar in Go routines and so forth. Oh, yes, sorry, forgot how I built this thing. Anyway. So one possibility is you can actually pass an error handling function to the channel as you construct it. So if an exception is thrown, that this function is called, the exception is passed to the function, and if it returns something non-nil, the equivalent of null, then that value will be put back on the channel. So this might be the way you do a default case, or it might be, as we'll see in a second, maybe a way of propagating the failure in some other fashion. One of the challenges with both of these systems is which call stack are we dealing with? If we actually are spread over several threads, then it's not obvious what call stack we really want to return. It gets kind of messy. So, and this is actually a general problem, right, with any multi-threaded sort of system where, how do we actually debug this thing if we have flow of control spread over several threads? So there's a couple of patterns that have emerged, and I should mention that a lot of this isn't really well documented in the core async community, so some of this is based on a private conversation I had with Alex Miller. So anything that's good about this, you give him credit. Anything I screw up, it's my fault, right? The usual thing. Well, one possibility is let's just propagate the exceptions back through the channel. So in a way, this is like sort of the way we think about stack-oriented programming, where we'll just pop the exception up the stack and then handle it somewhere where it's appropriate. But another thing that's commonly used is to just propagate errors to a custom error channel. Maybe that's going to trigger some downstream processing, and then whatever we want to do to recover on the upper end, we'll have to do. The last thing that's worth mentioning about this is you also have to be careful about deadlocks. If no one ever shows up on the backside to listen or to get the value, it's usually a good idea also specify a timeout so that you at least don't block the left-hand thread. So that's one way you could handle this, is one model of doing basically in process, on the fly, part of the domain logic kind of error handling. And on this point, I wanted to talk a little bit more about another model which does something mostly similar, which is reactive extensions. And we've already heard a lot about that already today, yesterday too a little bit. So the basic model is this. It's really very much a stream-oriented model where you have an event stream coming in asynchronously. It's going into what is essentially an observer that's watching the stream. But in the reactive extensions model, there's lots of operations we can apply to this stream inside the context of the observer, like mapping over things, filtering, flat mapping, all that kind of good stuff. The scheduler bit is just a way of controlling how streams are invoked and managed and so forth, without going into a lot of detail. And really, it pretty much follows the kind of standard ways that we've always handled exceptions, but it uses special operators as exceptional flow operators instead of just using try-catch clauses. But they're kind of analogous to that. So, source code alert. I think this should be valid. Actually, what language did I use here? I think this is supposed to be. I think it's supposed to be C#, but I'm not sure I've got it right. But anyway, I think it's not the actual syntax that has to compile; it's the ideas, right? I mean, well, anyway. So one possibility is to use this catch operator, which basically says that if an exception happens, then switch to this other stream I'm giving you. So that might be my backup stream, or maybe it's just the one I'm waiting for. It could be that I think this also gets invoked if the other stream ends, and maybe I'm just going to sequentially process a bunch of streams. But that's the possibility. And just a little bit more code. Once I've set up this stream, which is the subject that's feeding me data, and I have my observer that's going to be watching that stream and then doing whatever processing, then I stole this example from a website that's in the footnotes that you can get if you get the PDF. But anyway, I can keep putting data on the stream with onNext, and then if I put an error on it, in this case some exception, then it will trigger handling of from the other stream and just keep going. So that's one way I could do it. The other way I could do it is to specify a function for error handling, and also you can actually basically, like in normal catch clauses, you can say, I only want to look for these exceptions. If anything else happens, then pop up to the next higher level in the stack. So I might say that I'm going to be streaming whatever my type objects are. I'm going to handle my exceptions if those occur, and I had to abbreviate that to fit on the slide. But if that happens, then I'm going to do some triggering of this function that I just put as really as a comment that knows what to do with the exception to hopefully recover. So that's another level of control that I have. And there's also a finally clause. I didn't even put an example here, but it basically works just like a finally clause in regular code, where do whatever logic is in this clause. If I finish successfully, if I throw an exception, in either case, do what's in the finally clause. So maybe that's where I try to close down sources or whatever. There's a few more. There's one that kind of originated in VB called onErrorResumeNext, where you can basically, and I'm showing you two of the three function signatures for this one, where you can basically have like a list of streams that you're just going to keep reading from one at a time. If an exception happens, move to the next one and so forth. So you can do stuff like that. There's a lot of, I guess, debate about how good this particular implementation is, but nevertheless. And then the last one is a retry mechanism. So for example, if you expect that you're going to get hiccups because you're listening to a socket, the network may have glitches every now and then, but it can still recover and keep going, but you just want to keep trying and not give up. You can also use a retry operator, and you can even say only retry 4 times, so you don't get like a hot cycle of just continually trying something that's just broken and never coming back. So, but it basically boils down to the same sort of exception handling we're used to. It's all part of the domain logic, but it's a good way to handle these kind of small focused errors. And that's generally true for both of these models, that they sort of fit this model of let's focus on doing the right thing for this particular stream, but we're still missing something for like a global strategy that might be applicable over the whole application. Well, another thing we might try to do is prevent problems in the first place, when we can. And one of the ways to do that is to make sure that your model of what it is you're processing is as rigorous as possible and fits the kind of problem that you're working with. And one of the interesting things about this new reactive streams model that's emerged in the last year or so is it really embraces one of the key things that often happens in stream-oriented programming, which is that producers outrun consumers. And either I have an unbounded buffer, which eventually over time will overflow at some point, run out of memory, or I have a bounded buffer, but I have a feedback mechanism that I can send control messages back to the producers to titrate how fast I'm getting data sent through. So that's the idea here, is that we can sort of globally strategize about how to manage the overall flow of data rather than just have each stream kind of make its own ad hoc decisions when things go out of control. So that's one thing we'd like to do, is make sure our system is making first class the kind of problems that we always encounter, like streams getting ahead of consumers, or potentially getting ahead of them. So the cool thing is, though, somewhere I might have to make a decision like I need to drop data because there's nowhere for it to go, or I happen to know that in this particular point I can inject flushing to disk and then drain that disk file later on. But at least you can make that decision strategically. You're not just sort of ad hoc making it in the context of some small stream somewhere in a larger system. Well, the other thing we might try is to use the type system to also enforce correctness as best we can. Now, this isn't going to help us with like network drops or someone forklift the power cable going into the data center. We're not going to prevent those kind of problems with types, but nevertheless, we can make our code more robust as a result. And there's a couple of ways to think about this. One is to express what is really going on in the code, not just what you think is going on. For example, suppose the code raises exceptions. Well, rather than just return some item, like an order in this case is this contrived example, why don't I wrap it in this try object that tells the reader explicitly in the type signature, you're either going to get something successful coming back, or you're going to get a failure that wraps whatever exception is likely to happen, or that I think is likely to happen. So just by reading the type signature of this parse method, and the little example here is something that might be getting, say, orders for an e-commerce site as strings, because we all know how important it is to exchange data as raw strings. So I just want to parse it, but I'm being very paranoid that I may get some bad string in here. So what I'm going to do is return a try wrapping the order object. If I succeed, I'm going to return something. This try clause will actually, notice the capital T, it's actually a constructor. It's going to return a subclass called success. This is from Scala, obviously. I can hear the feedback. But if it fails, if I raise an exception, it'll return something called a failure object. And then the reader, or the caller of this method, can then do the right thing to decide, all right, what do I do? If it fails, maybe I ignore it. If it succeeds, whatever. And the other way, another thing that we could embed in our type signatures is if we know we have latency, then let's use futures. Now, of course, we tend to think of using futures as just a way to get better performance, better utilization of our threads. But it also has this benefit of communicating to the reader that there's something with reasonably high or probably high latency going on, and therefore I'm going to do this asynchronously. So I might, back on this sort of idea of e-commerce, I might have a user account, and then I'm going to get that asynchronously from some database. For a given ID, I'll retrieve the account information, and then maybe once I have the account, I'll retrieve their orders to do some processing. But the great thing about this, and this is also true for try, is that I can go back and write what looks like synchronous code, and it is sort of synchronous because each of these will happen one at a time. That the get orders will not happen until the get account is returned. But the nice thing is that I can construct these monadically, if I can use that overused word. And I have very easy to understand code, but it's actually invoking these things asynchronously and not tying up threads while it's doing these blocking operations. So we both get better performance, but we also get more expressive code about what's actually going on, in this case, dealing with latency.
It's actually not supposed to be parallel.
Pardon me?
It's not supposed to be parallel because, orders wouldn't be called unless accounts would be calculated.
Yeah, so I mentioned that actually. So in this case, it will do one at a time. Yeah, so get account will call, and when it returns, when it finishes, then it will call the next one. So that's very true. And I picked this example specifically because I can't actually run these in parallel. I need to get the account before I can get the orders anyway. But the point being that I can write what looks like sequential code, but it is actually going to use the threads efficiently, even though it has to do blocking operations. That was kind of the point. Okay. All right. And basically, this is really kind of similar to what you would do with Go blocks and core async or Go routines. You could do something very similar in construct to this. So what am I doing here? Let's see. Well, just another way I could handle these futures is actually use callbacks, which, you know, that works fine if you don't have to compose a lot of them together, but sometimes it's more efficient and more explicit to just say, well, get the results, and when you're done, call these other methods that are going to continue the processing as an alternative. Well, the other way you can use types is to try to enforce correctness, not just to convey to the reader what's actually going on. And this, I kind of use this as a tie-in to talk about briefly functional reactive programming. The idea with functional reactive programming, which emerged out of the Haskell community and has been ported to JavaScript with the Elm language, is that I want to model the case where I've got state that depends on other state, and that other state is going to be evolving in time, but I want to propagate those dependencies to my new state in a way that doesn't require a lot of sort of standard imperative coding. This is an example from a research paper. Nobody actually uses the Scala dialect, but the reason I used it was I figured it was easy enough to understand what's going on without trying to show an example from Haskell or Elm. But basically, the idea is this, that I'm going to track on the mouse down, the initial mouse down movement, and that's going to be where I set up my reactor, as they called it in this API. And then I'm going to keep looping over the mouse events until I get a mouse up. And every time I get an event pulled to me, I'm going to draw a line from the original point to the current point. So, it's the kind of thing we've done all the time with graphical toolkits like drawing tools, where we start a line and then keep moving the mouse around until we hit an end line. I really don't want to write all that imperative code to do the calculation of the new line and all the dimensions. I really want that to be handled as much as possible by the system. So internally, the idea with these toolkits is that they're tracking all this mutating state, but they're actually modeling it as time series data. So I had an interesting conversation after Jonas's talk with somebody. He mentioned the idea of time as sort of a first-class concept. And what does that really mean? In fact, I've been using the idea of errors as a first-class concept. Well, ideally, what it really means is that inherently everything we do has a notion of time attached to it. I don't need to keep track of mouse down at what particular timestamp. It's just all part of the system. And internally, it's all treated as like a flow of immutable data where each change is actually a new timestamp and a new event, or in this case, the location of the mouse. And then I have logic that keeps whatever view I need of that current state of the data up to date without me having to do a lot of hand coding. So that's sort of the idea. Another way to think of this is kind of a data flow model, where I have dependencies between, in this case, where the line is, and that depends on where the mouse is. But as much as possible, I'm letting the system manage that dependency for me so that I can minimize the chance of screwing it up myself. All right. But on this point, because it came out of Haskell, a lot of it was really inspired by, can we represent something that seems so inherently mutable as an immutable idea? And the idea they came up with was this time evolution. And then being Haskell, they really emphasized getting the types right. And there's an interesting paper that tries to look at how you could avoid even more problems that might crop up in a reactive system by getting the type signatures right, among other things. So if you're interested in that kind of stuff. Now, obviously, once again, this is not going to stop or handle network failures or data centers going down. But hopefully we can squeeze out as many of the bugs as possible. As I started working on this talk, it kind of evolved into half, let's talk about how you handle errors, and half, how do you actually prevent them in the first place? I think maybe that's where it kind of went. Well, the last big section is, what do we do about managing errors? Is there another way besides just having that logic embedded with the code? The domain logic. And one way to do it is to have completely dedicated separate modules that are responsible for life cycle of our applications, that handle the cases of failure, that handle recovery, and so forth. And the best example of this we have right now is the actor model. You know, I didn't tell you where these slides came from, the pictures, did I? This is actually an astronomy observatory in Jaipur, India. It was built by one of the Shahs back in 1720. So I think these particular devices are for looking at the constellations in the horoscope. Anyway, it's a really cool place. If you ever happen to be in the neighborhood, you know, check it out. All right, and anyway, so let's talk about the actor model. So just sort of schematically, each actor has a mailbox, and it's all an asynchronous system. So when one actor sends a message to another, it goes at the end of this queue, and then the actor processes each mailbox entry one at a time, and the system guarantees that that processing is thread safe, so I don't have to worry about, you know, the actor code being invoked twice on the second message, and now suddenly I've got you know, a thread safety issue. So the idea is that you could actually embed logic like state mutation inside an actor, let the actor manage it, and it's thread safe. This actor ref bit is something that Akka added, which solves an interesting problem, which we're going to get to in a minute, which is what if the actor goes down and I decide to restart it? Now, I would have all these dangling references to a dead actor. But if the actor ref is just this very lightweight, highly durable thing that's, you know, basically a handle to the real actor, then I can reconstruct the actor on the back end and the references are still good. So that's the idea. And it's one of the things that was introduced into the Akka actor model fairly early. All right, and I can hear the wind picking up. But you can see that it's kind of superficially similar to channels in the sense that I have this bounded queue, or potentially bounded, it could be unbounded, and then I'm sending messages in one end and I'm pulling them out the other. So we're going to play on that here in a second. Yeah. So what does an actor do? Well, basically, it can do one of three things, or a combination of these. It can send other messages to other actors, or even send back a response to the original actor. It can also create new actors if it wants. And one of the interesting things, it can even change its behavior, which is really a state change. So you can implement state machines really nicely like this, where, and a classic example actually is, maybe there's some initialization I have to do in my actor code. So on the very first message, maybe the only one I'm willing to accept initially is a, you know, start yourself message, and then I transition to a state that's already initialized and does subsequent processing. One of the key differences, though, with the sort of the default channel model in CSP is that this is entirely asynchronous. That I'm sending messages, you know, as we'll see, that I can do some synchronicity, but nevertheless, as soon as I send a message, the flow of control returns to me, and at some point down the road, that actor is going to handle the message. Also, an interesting trade-off here is that typically these systems are untyped. So the actors have to be able to handle anything they receive. We'll talk about that as a problem in a second. One of the interesting things, though, is that these models are actually dual, and that's a fancy way of saying that they actually have a lot of synergies, but at the same time, they sort of take opposite perspectives on things. What does that mean? Well, for example, by default, CSP channels, or processes is actually the term in the original theory, is they're anonymous. So, you know, I have this nice clean separation, almost like a black wall. I don't know who's on the other end of this channel, but I'm just, you know, talking anonymously to somebody. Whereas on the other hand, actors, well, did I say that? Yeah, so actors have identities. So they typically, you know who you're talking to on the other end. CSP messaging is essentially synchronous. We saw that if you have more than one spots in your channel, that it effectively behaves asynchronously. But it's really designed to be a synchronous model where there's a rendezvous process between the putter and the getter, whereas actors are completely asynchronous. On the other hand, though, you can actually implement either one in the other. I said that right. So for example, and I said this earlier, you know, the channel and the mailbox for the CSP versus actors, they kind of look very similar superficially. And it turns out that you can kind of do the same things that you like about the other system. So if you like anonymity, you can actually get that in an actor system by putting, you know, another level of indirection, which is like a lookup service. You know, I need to get somebody that knows how to talk to the database, and you get this address for an actor, and then you talk to it without really like hard coding anything about that actual actor address. And that actually gives you the benefit too of, you know, maybe that actor you're talking to is actually on another machine somewhere. Conversely, typically the way these CSP implementations work, you actually are sharing some identity of a channel, so it's not as anonymous as the model implies in practical terms. I said CSP messaging is synchronous and actors are asynchronous. Well, most actor models give you the ability to send a synchronous message where you're just going to block until a response comes back. So when you need to do that, you can. That doesn't scale as well, but that's a possibility. And similarly, because you can have these these buffers that are bigger than one element, you can also have essentially asynchronous channels too. So I hope you get a sense that they're actually kind of sort of two sides of the same coin in some respects. Well, two of the real systems, the main systems that were actually implemented that extend the original actor model in some important ways are Erlang and Akka. And in particular, they both do two very important things, one of which is that they allow you to do distributed actor systems, so you can actually build a cluster of machines and then move processing around as you see fit. And this generalizes the notion of actor identity, too, from being just a point in memory to like a URL that I'm talking to. But the other problem is that it adds a lot more failure modes that you have to handle. Obviously, now you're introducing all the usual network problems. So that brings us to the second point, which is maybe the best innovation in the actor model, the one that is maybe the most exciting thing about it compared to CSP, is that it has really let's call it the industry's best model for handling failure. And that is this idea of embracing failure or letting it crash, where if an actor goes down, rather than trying to embed recovery logic within the actor, let's just let it go down, but let's know how to reconstruct it, know how to detect that it failed, and then rebuild it. And it was Erlang that introduced this idea of supervisors, which are themselves actors, but their sole responsibility, usually anyway, is life cycle management of their children, their subordinates. And this is, it's a completely transparent mechanism, so it works really well over a distributed system as well as a local system, subject to all the usual issues of distributed communication and so forth. So, if one of my actors dies and it takes its children with it, then I can decide, strategically when I construct this hierarchy of actors, what am I going to do? Do I just let them go down and not try to reconstruct them? Do I tear down the entire subtree and reconstruct everything? Or maybe I just rebuild the actors that failed. But I have that choice. I can just do that, and it works generally really well. So Erlang kind of emerged out of the telecom industry, right? It was invented at Ericsson by Joe Armstrong and his collaborators. And what they were trying to build was extremely reliable telecom switches. And if you think about this model in that context, it's really a beautifully perfect fit, because typically what you have in a telecom switch is like thousands and thousands of concurrent phone calls, each of which I want to manage separately and independently of the others. And they don't actually talk very much to each other. You actually don't want to hear what other people are saying on their calls, right? But what happens if a session goes down? Oftentimes you can reconstruct the session before the user actually notices that it's gone. I mean, they might hear, are you still there kind of thing. But often you can reconstruct it. So actually embracing failure, not trying to recover, just tear it down and rebuild it as quickly as possible. It works beautifully for that model. And you can generalize this for like session management in the web and a lot of other applications. So we've kind of figured out that you can only take in-process recovery so far. You almost never think of all the possibilities. In a given context, you rarely have all the information you need to make strategic decisions about what to do. So just saying, I'm not going to do that, I'm just going to punt on this tree of processing, but have a way of monitoring it and reconstructing it quickly, is a much more robust model. And he has this, a bunch of things like we can be very strategic about error handling, and we can even plug in different error handling for different contexts, even adjust it on the fly as needed. And it gives us a nice separation of concerns between normal processing and error logic. But yeah, so it's just a very flexible and powerful way to do this. Now I have to mention there's some criticisms of actors, and I just want to go into this briefly, not so much really to try to defend actors, because I don't think they need it, but just to mostly emphasize the duality of these things is not quite as extreme as some critics might say. So I'm not going to read this Rich Hickey quote, but he's sort of the famous guy that likes to criticize actors and specifically chose not to put them in core async. Actually, a better list is a guy named Tim Baldridge, who has done a lot of work with core async in the Clojure community. So he complains, well, you've got these unbounded queues, these mailboxes, so you've got the whole out-of-memory problem. you're basically mutating state inside these actor things. Isn't that supposed to be bad? I mean, we're supposed to be in a functional world, right, where we never mutate state. If you want to see the state of something, you have to send a message to an actor, and you ask, well, what if the mailbox is backed up and I can't get to it? Also, they complain that you're coupling a bunch of things together, like the producer, the consumer, and this channel in the middle. That seems bad. And then finally, it's effectively you're doing asynchronous object-oriented programming. And we all know that that's a failed idea, right? We should never do object-oriented programming anymore, right? And I'll add this, that they're untyped, or at least most systems are untyped. So you have to exercise extra caution with the messages coming into your actor. And wouldn't it be great if we could have type safety for the messages coming over? So just briefly, what are some answers to this? Well, there's no reason you can't have bounded queues. That's pretty much standard now. Some of the criticisms were kind of based on toy examples. But we can pretty much do all of this we want. And we just talked about reactive streams as the, if you put in bounded queues, what are you going to do when things fill up? Well, you do something strategic, which is you manage the flow across the entire system and make decisions in the right places about what to do when you cannot service all of the data coming in. So this is going to basically address that problem. And because it's a layer on top of systems like Akka, you can do things like impose type safety. You can put operators on the streams like RX and so forth. So if you in some ways think of Akka as like the assembly language of reactive streams, then you get a lot of the benefits of reactive streams, and you get this amazing supervisor hierarchy for managing failure. The fact that we're mutating internal state was actually the whole idea in the first place, that we're encapsulating state in well-defined boundaries. Joe Armstrong jokes that Erlang is an object-oriented language for this reason. Even though it's pure functional, it really has this notion of I've got state inside, and I can actually mutate the state by changing the behavior of my actor. So if it responds a different way to the next message, it's effectively a state change. But I can do it in a very controlled, very firewalled way. So this is actually what we want to do. We actually want to embrace, when we need to have mutating state, we need a strategic way to do it. Yes. Also, the fact that we're sending messages to get state, well, maybe it's true. You might end up with a backed up actor and all that stuff. But most of the time, it really doesn't give you a clean separation between this, like command and query, where I want to know one place to go to get the current state. I don't want to have that state cached all over the place when I can avoid it. For performance reasons, we all know we cache state, but when we can avoid it, when I know I can ask this guy over here what the state is, then that's actually an advantage. And all of these things can be decoupled too, so that's not really an issue. And the final one is, what about the typed actor, the fact that they're untyped? Well, there have been attempts to write typed actor systems. We actually tried that in Akka, and it didn't really work out. But actually the way I think about actors, I really think of them as extremely lightweight processes. In the same way that I think we kind of need to re-embrace the notion of an operating system process. It's a really great modularity tool. I think Ben kind of got into this a little bit yesterday. It's a beautiful boundary. You know exactly where the boundary is. You have very fine-grained, controlled inputs and outputs. Yes, you have to do some very, paranoid checking of the stuff that's coming into you, but it's actually, I actually think of actors as processes. Now, you can actually spin up millions of these things, right? But I wouldn't normally do that unless they were like workers that are completely stateless, and I know that they're basically all the same. But I actually think that if you think of actors as processes and how you would write system processes, then a lot of these issues, for me anyway, go away. But nevertheless, there actually is a project in Akka to rethink doing typing with taking those references I mentioned and make those types, or typed, so that I can only send messages of a given type to an actor, even though inside it might be typeless in a sense, but the interface that I'm actually talking to does have a type. All right, so to kind of wrap this up, how should we really handle failures in these systems? I think it's great to do what we can in fine-grained scopes, like what we described with RX extensions, with FRP and so forth. But real systems need some sort of strategy for error handling, for failure recovery. And I think the best thing we have is either actors or the system that Ben mentioned yesterday, something like Hystrix, which I happened to find this week before I even talked about it, so that was fortuitous. But it's really a clean separation of concerns. It gives us Make sure that came up, yes. So we get, nice separation of concerns. We've got management over here. We've got the workers over here. And just like our corporations, they don't get along. Now, wait, I don't want to take that too far. Anyway, so that's what we need. We need that kind of separation. We can delegate failure handling to components that have that strategic view and know what to do. We can plug and play different strategies as needed. And it gives us better scalability over large systems. All right, so to wrap up, that was a giant sundial, by the way. It's like, you can see each of these windows is probably like 2 stories tall, so it was maybe 100 feet tall, this big sundial. Anyway, the disadvantage of actors, at least as of today, they're kind of untyped interfaces. They really are kind of more object-oriented than functional, and we all know that functional programming is the way God made the earth, right? So, and I'm sorry, is someone going to question that? Oh, it's logic-oriented. What are you talking about? And there is higher overhead, just the actor infrastructure, even though it's fairly lightweight. On the plus side, we have really the industry's best proven mechanism for global error handling and recovery, as far as building applications that are rock solid. And Ericsson's telecom switches are a great example of this. And we get native asynchrony just by the model itself, the way it works. So in a way, it is the best we have for that sort of error handling. But there are alternatives like Hystrix so that we can use tools like reactive extensions that don't give us this kind of global strategy, but we can get the best of both worlds by combining different systems. And if you want to argue with me, well, I'd really like to have something focused on that stream kind of stuff, and then some other entirely different system managing the big picture, that's a perfectly fine argument. You don't necessarily have to have one comprehensive picture like actors to do it all. So the disadvantages, though, of CSP and RX and those things are that they only cover error handling to a limited scope. They haven't really implemented distributed channels in sort of a global way. I mean, you can certainly have channels that are actually sockets crossing a network, but not in the sort of distributed clustered channel model. But on the other hand, the advantages are they really emphasize the flow of control, the passing, either data streaming or I'm actually passing control over these channels for different processing purposes. And they do embrace typing a little better than most of the actor models. And since we're in a comedy club, I wanted to finish by saying that you've been a great audience. I'm here all day. Don't forget to tip your waitress and try the veal. So, thank you very much.